ஆன் பண்ணுங்க இவனா
Hello.
Kanickai Raj, just one minute. I present Raki and hello, Kanickai Raj. I present the marketing and desktop or chat. Desktop 3 da. Okay, so yeah, okay. Okay, yeah.
டெஸ்க்டாப் பண்ண போறாரு
Start from. Oh, okay.
Very pleasant. A very pleasant morning to one and all. On behalf of Department of St. Joseph's College, we welcome you all for the second day international webinar on materials and technology for sustainable development. In the first session, Dr. Bhaskar Sundar Raju will address on clean catalysis for sustainable development. The second session, Dr. S. Chandrasekhar from China will address on construction of stable duplex by acyclic nucleic acids. Before we start the first session, let us start with prayer. With God, we are heroes. Without God, we are zeros. To invoke the blessings of God, may I now invite our Reverend Brother O.P. Santosh of our Chemistry Department to invoke the presence of God. Welcome, brother.
Good morning to everyone. Let's gracefully begin the day by invoking God's grace to be with us today and in the days to come. Now, let's all listen to a reading from the Bible. A reading from the Holy Gospel according to St. Matthew. You are salt for the earth. But if salt loses its taste, what can make it salty again? It's good for nothing and can only be thrown out to be trampled under people's feet. You are light for the world. A city built on a hilltop cannot be hidden. No one lights a lamp to put it under a tub. They put it on the lampstand where it shines for everyone in the house. The same way, your light must shine in people's sight, so that, seeing your good works, they may give praise to your Father in heaven. This is the gospel of the Lord. Praise to you, our Lord Jesus Christ. Let's spend a few moments in prayerful silence, assimilating the spirit of the reading that we have just heard. At present, COVID-19 pandemic has significantly transformed the way we approach life. This pandemic leads us to some painful insights that we, the human beings, are all permanent victims of inscrutable forces that are beyond our control. We are confronted with the true uncertainty of human existence and the true vulnerability of human life. Presently, millions of brothers and sisters, especially the migrant workers, the homeless, and the destitute in our country, are despairingly worn out with intolerable suffering and hardship. It is in this situation of frustration and ferment God invites each one of us to be salt and light for the world full of people in need. Salt does not add flavor to itself, and the light does not illuminate itself. Instead, both are essentially for others. We, being salt and light of the world, are called to illuminate the darkness of despair of people by preserving and seasoning the well-being of all, especially the life of those in the midst of misery and hopelessness. Let's all embrace the invitation to make a difference in the world. Now, let's all close our eyes and pray. God the Father, the most merciful and ever-loving God, thank you for inviting us to be salt and a light for the world. During this pandemic, being painfully mindful of the cry of the poor, the voiceless, and the exploited, which is too loud, alarming everywhere, we desperately stretch out our hands to you so as to take refuge in you. Today, we all come together for a purposeful intellectual discussion which may substantially drive us to be able to sincerely use all our scientific knowledge and intellectual capability to reduce the pain of humanity. Thus, Lord, bless this event, bless all the speakers of the day and the organizers of the event, bless the management and the Department of Chemistry, and bless all the participants of this webinar so that we may be able to feel that our response to the needy world is not only possible but also necessary. We ask this through our Lord Jesus Christ. Amen.
Thank you, brother. Soft skill trainer, IIT CSER examination trainer, active researcher, also one of the organizers of this 2 days international webinar is none other than our young and energetic professor of our chemistry department, Dr. A. Irudaya Jyoti. I take immense pleasure to invite him to introduce the today's topic as well as today's resource person, Dr. Bhaskar Sundar Raju, IIT Kanpur. May now invite Dr. A. Irudaya Jyoti to welcome the gathering and introduce the speaker. We welcome you, sir.
A very good morning to all of you. Respected head of the department, Reverend Fathers, brothers, respected faculty members, researchers, scientists, participants in India and abroad, a very good morning to all of you. It's with great pleasure I welcome you all to this second day of the international webinar on materials and technology for sustainable development. It's again with great pleasure I welcome Dr. A. Peter Pascal Regis, our beloved head of the department, Dr. S. Bhaskar, the Associate Professor of IIT Kanpur, the today's speaker, Dr. S. Chandrasekhar from Sonshan Institute of Advanced Study, China, Dr. R. Venice, Dr. Dean, IUKAC, and the organizing secretary of this international webinar. The organizing secretaries of this international webinar, Dr. A. Simi, Dr. I. Kanickai Raj, respected faculty members, and participants. I welcome you all again for this second day international webinar. With great pleasure and indeed with much happiness, I'm very happy to introduce today's speaker, Dr. S. Bhaskar. Bhaskar studied here in our department in the year 2006 and 2007 for his MSc and graduated here, and again he went to University Rennes to do his Masters International. He is the one who opened the doors of University of Rennes to the students of St. Joseph's, to which at least 10 of our students followed him to do their master's degree in Rennes. After his second master's degree in Rennes, he did his postdoctoral researcher fellowship in Max Planck Institute for Coal Research, Germany. As soon as he completed his PDF, he joined as a faculty in the Department of Chemistry, IIT Kanpur in the year 2013. He is promoted to the associateship in the year 2018. He has been a starter in the institute in the field of catalysis. The awards and recognitions that he has achieved during a short span of time is very overwhelming. He is the winner of Merck Young Scientist Award of 2019, a very prestigious award. And he has been there in the top 3 finalists for the Scopus Young Scientist Award in 2019, and he is the Best Young Faculty Research Award from the IIT Kanpur in 2017. He is again been awarded with DAE Young Scientist Research Award in the year 2014 and Theme Chemistry Journal Award 2014 and AVH Fellow 2012-13. And he has been part of many committee members, Selection Committee member for Reaxis PhD Prize 2019, International Advisory Board member for Open Access Journal INEOS 2019, is the Associate Editor of Journal of Heterocyclic Chemistry from 2019, and he is an Early Career Advisory Board member by ACS Catalysis from 2018 and 19, and is been invited to be part of Linda Nobel Laureate meeting for chemistry in 2013. To his research credit, he has published nearly 50 research articles in reputed international journals. With all his intellectual, academic, and research capability, we are very fortunate to have him as our proud alumnus of our department. On behalf of the department, the college management, and the organizing committee of the international webinar, I welcome Dr. Bhaskar to take up the session and deliver your address. Thank you very much, Bhaskar. Over to Bhaskar. Thank you.
Okay, so I hope I'm audible to everybody. At the outset, let me first thank the St. Joseph's Chemistry Department in particular. And so in addition, I also I have a lot of respect to the head of the department, Dr. Pascal Regis, as well as other faculty members, including Dr. Jyoti, with whom I have a lot of friendship I had over the period of, let's say, about 10 years now, right? So let me actually begin my talk today by asking this particular question. So does clean catalysis actually matters in sustainable development? So, of course, it's a buzzword. If you really look at the catalysis in general, let's say it is there actually for more than a century, and sustainability is the buzzword actually now everybody uses actually around the world for every matters. So my question to actually the audience as well as actually to the common people in general is that is it really required actually to do a catalyst actually to do any transformation? If so, how those actually catalysts will actually going to impact on our actually daily day-to-day life, right? So that's the question actually I'm trying to actually ask myself, okay? And actually in the process of actually next 30 minutes, I will try to actually convince you that perhaps it is the time that we need to look into the reactions or actually any transformation which we do has to be very clean, and it cannot actually afford to have any side product at the end of the reaction, okay? So before actually I take you all actually to the chemistry first, and I really would like to actually ask myself, or I would like to educate myself actually what is meant by sustainable, and I also actually try to actually see how does actually that is going to connect to chemistry, and in particular actually to life, for example, right? So I just quickly actually gone through on the web. I tried to see what is the meaning of actual sustainability, okay? So it says that the ability to be maintained at a certain rate or a level, or it can also actually say that in chemistry point of view, let's say avoidance of a depletion of a natural resource in order to maintain an ecological, let's say, balance, right? So if this is really true, right? So how do you actually define, how do you actually classify, let's say, sustainability? So in a larger context, sustainability was actually classified into 3 different ways. So let's say economy, society, and environment. Perhaps I'm not good enough actually to talk about the economy or society, for example, but certainly at least I would like to educate myself as well as others, on the environmental aspect and how actually chemistry plays a crucial role actually on the environment, right? So we look at actually 2 actually major aspects. One is energy, and the second one is, let's say, reduced emission of greenhouse gases, right? So if you look at the energy which we use on day-to-day basis, right? So it could be electric current, it could be mechanical or electrical, for example. So any energy which we consume or which we use in a day-to-day basis has to be very clean, and it needs to be renewable, right? If it is not actually renewable, of course it is going to have an impact, if not now, let's say in down the years, right? So, and is that energy is so efficient? If so, can we actually be more clean? That is a question that I really asked myself. And then actually it comes, so let's say, for example, if we make use of natural resources, and then we actually try to consume those natural resources as an energy to do a transport, for example. So what we actually do in actually impact is that you will actually try to produce a lot of amount of, let's say, greenhouse gas such as actually CO2, right? So we all know actually how the CO2 plays a crucial role to balance our life, as well as actually it is actually going to harm in case if we actually increase along the rate of the CO2 emission. Okay. So what are the materials actually which you believe is going to be renewable resources, and how actually those renewable resources can be utilized in an atom mechanical manner so that it is going to be impact on our day-to-day life. Let's say. So there is another buzzword which was coined in the recent times called circular economy. Okay, so what is one day circular economy? Let's say, for example, you start up with a resource, and this resource should be actually biocompatible. If that is true, right? So what you actually take as a starting material comes from the biocompatible resource and goes into a manufacturing process, and then it actually comes out as a product which will be used actually by the consumers, and which after the consumer use. Most of the times we know very well actually this goes to actually environment as a waste, right? If we somehow will find a way to actually take this waste and then actually recycle it back into a starting material, then it can go further actually back into a manufacturing process, and that's why people tend to call it as a circular economy, right? So let's actually move on actually to materials and chemicals which are actually required or which are useful actually in our day-to-day life. So if you look at the source of actually chemicals which we apply and on a day-to-day basis is actually comes from most of the time with fossil fuels, right? So this exclusive dependent of fossil fuels also very dangerous, because the reason is that fossil fuels availability on Earth is perhaps not actually going to be there for next more than 50 years, right? So that means you need to look for an alternative source for these chemicals and materials. Otherwise, we will running out of source, and thereby we will not be in a position to continue the chemical processes which we do actually currently right now, right? So that means sustainability is a key for concerns of science, technology, industry, and as well as the society in larger perspective. So, and that's where the concept of green chemistry came in, let's say, at the early of 21st century, right, which involves the green solvent, green catalysis, efficient processes, and of course, green and renewable raw materials so that it can be recycled, right? So, me as a chemist, I ask, can chemicals and materials needs of mankind based on, let's say, the concept of sustainability, both resources as well as environment? That's the key question I will ask myself, right? So let's move into where the sources actually come from. Let's assume that the crude oil which is actually produced in the Middle East countries, right? And these crude oils actually goes for a fractional distillation. Let's say, for example, at an industrial scale, and coming out of this fractional distillation, most of the oil which actually comes out of this will actually go for actually energy, and remaining, let's say, about 7% actually goes as a feedstock. And what is this feedstock means? These feedstock chemicals actually converted further back into a polymer which we actually use every day, for example, in the form of chair or actually any other materials which are actually mostly made up of polymers, or it can be a commodity chemicals, and these commodity chemicals can be used as a fine chemicals, or let's say, for example, it can be converted into pharmaceuticals which we actually consume on every day-to-day basis as a drugs, right? So, how do we actually try to, let's say, look for an alternative source so that actually we do not actually depend largely on actually crude oil? So, of course, one of the alternative option actually for not depending on crude oil is actually try to see, let's say, for example, the abundant source of CO2 into methanol. If that actually happens, if you also find a way to produce, let's say, hydrogen from methanol, then this will be the cleanest energy source, and thereby we will not, for example, depend largely on the crude oil, right? Today my talk is mostly depend on actually these particular parameters, actually talking about actually specialty fine chemicals, pharmaceuticals, and how do we actually say design a catalyst to do this actually transformation, right? If you look back in the literature and especially the textbook, what we will see is that most of the transformations which were actually done for the preparation of fine chemicals or pharmaceuticals are largely actually done with the help of the transition metals, right? If this is really true, what is the background and how actually this transition metal organometallic chemistry grown over the period of, let's say, a century? Okay, so that's what I can try to give a small history of how the organometallic chemistry grown over the period of 100 years. Right, this is what I started at the beginning of, let's say, 20th century. So what we will see is the concept of Oswald and then later actually Sabatier hydrogenation, which actually opens a wider opportunity for reducing, let's say, a lot of unsaturated compounds into saturated compounds, which could be used actually for wider applications. And then the most important actually process which is actually developed by Haber, which is actually going to have a balance in our lifestyle, which is nothing but an ammonia Haber process. And later actually we all know, how Ziegler's contribution in terms of, let's say, polymer synthesis in 1958, which eventually gets a Nobel Prize actually for in 1953 in a very short span of time. And for organometallic chemistry, how metallurgy actually going to have an impact, let's say, by the discovery of Fischer and Wilkinson on the synthesis of actually, let's say, corrosive, right? So if I actually look back at these people, I really give a lot of respect to these scientists. It's because of these scientists, what we actually see as a matured organometallic chemistry and catalysis applications, it's purely because of these people's curiosity over the century, right? So, and if you look at it very closely, you will clearly see it is actually most of the times these processes have been developed from the transition metal chemistry, which means that you will be able to actually see the use of transition metal chemistry in all the processes which I have described just now, right? So let's say you actually plant a tree, right? The tree will actually definitely give a fruit actually one day for sure, right? This is the same way in the 1900 and the tree of the seed of organometallic chemistry was actually planted, and the fruit actually is really achieved, let's say, by the early of 21st century, which you will clearly see a remarkable achievement of various organometallic chemists, and that fetched a Nobel Prize in 10 years time, right? 2001 asymmetric catalysis actually by 3 Nobel laureates, which I do not actually go into the details of their name. I suppose everybody knows it. And in 2005, a little bit of this is yeah. Okay. Otherwise, I can put up the mic.
No, we can hear you.
Okay.
You can hear, right?
Yes. Hello. What's the phone money?
I think I will go without mic, but then I can go closer. Yeah, so I suppose you will be able to hear me properly now, right?
Okay.
Yeah, so I think it's better.
It's okay, sir. Continue, sir.
So in 2005, the Nobel Prize was actually given to olefin metathesis and for three Richard Schrock, Grabs Leslie, and Xiu Chawan. And in 2010, it was actually given to three gentlemen who really contributed to cross-coupling reactions. And their contributions are actually well applicable in several fields, and that's why eventually they get a Nobel Prize, right? Although it is debatable, there are quite a lot of people deserve to be in that particular list. But the Nobel Committee always decides to give only 3 prizes for any topic, right? So let's move on to the success of catalysis, how the timeline of the organometallic chemistry evolved over the period of time. So we consider the 1900 is in the early days of organometallics, and the major discoveries are happens between 1900 and 2000. And the transition metal catalysis, really overwhelmingly grown, during this 110 years time. But we will clearly see, among the transition metals, it is mostly the noble metals which were actually utilized, and those noble metals were, you will actually see in a minute that their availability in the earth crust is actually questionable, right? So that's when around 2012 the base metal 3D metal catalysis actually came into the picture, and so you will actually see why 3D metal catalysis is important, and how this particular thing will take forward for next century, right? So we at IIT Kanpur what started our independent program, let's say at 2013, and we actually question ourselves, where do we start, and how much our research is going to impact on our daily day-to-day life, and if so, and the catalyst or the organometallic complex which we develop, will that going to sustain for a longer period of time, or only for a shorter period of time, or only with respect to publications, right? So this is the question we asked ourselves, and we felt that it is the time that we move on with the noble metals. We try to look for metals which are very much abundant in the earth crust. So we felt iron, nickel, and cobalt are the 3 metals which are coming from the transition metals, but in 3D transition metals rather than the 4D and 5D. So let's get into the details. Let's say, for example, if the metals come from 4D and 5D, in particular, let's say ruthenium, rhodium, palladium, osmium, iridium, and platinum, you will actually see almost 3 out of 4 reactions or transformations which happens today are coming from these metals, right? If we understand from the textbook that these metals most often goes for a 2-electron process, which means metal 0 will oxidize into metal 2, and metal 2 will oxidize into metal 4, right? That is the way these transition metals, especially 4D and 5D, will operate, right? So, but if you look at the 3D transition metals, we know that it can go either for 1-electron oxidation or a 2-electron oxidation, depends on the reaction conditions, right? If this is really true, right? So of course, if the nature always gives inspiration to us, and nature always takes material which are very much sustainable. Okay, if you take any process, nature always takes a material which is very much sustainable. So, in other words, nature makes sure that the material which we used will come back again to the environment, and then that will be recycled, so that it is going to have a huge impact on the circular economy, right? So, and the metals which are applied in most of the enzymatic reactions, which happens at a very high Chernobyl number, are coming from the 3D transition metals, and does not come from 4D and 5D. So, which clearly indicates that the 3D transition metals are more sustainable compared with, let's say, 4D and 5D. Right, so that's when we ask a question ourselves. So let's say, can modern alchemy metamorphose the function of a base metal to surpass the precious metals? Right, so that's the question we ask ourselves. So our group largely, work on 3 different aspects. One is to see how they define, design a ligand which can have a huge impact on the electronic property of the metal, and that going to have an impact on catalytic outcome. So we largely would like to work on a high valent metal. I will also explain why we need to work on a high valent metal. And often we try to have some curiosity or the concept in mind, and we try to get in contact with the people, to try to at least see whether these processes are actually viable, through DFT calculations, and if these actually help us, then we will actually take up those concepts to the experimental, and then subsequently we try to actually do a chemistry of it. So, but having said that, so our group do not actually consider to see metal complex as a metal complex. We try to actually see those actually metal complex as a catalyst. So which means we have actually application in mind to take this cyclic complex and try to actually see a real-time applications, so that actually we will not actually only fascinated about the structures of those complex. Actually, those days are gone, right? Anything you actually do, you try to actually see there is an application. If there is no application, there is absolutely no fun of actually doing that. That's what actually my philosophy is, right? So, and there one of the applications which we actually wanted to see is that, let's say, for example, to make any actually biologically active compounds or natural products, or even, let's say, for example, drug molecules. If one particular drug molecule is available, you want to actually test, let's say, 100 different actually derivatives of actually those compounds, then you need to actually synthesize actually those drug compounds or the derivatives of those drug compounds actually starting from scratch. So my first concern or question is that, can we try to, let's say, for example, use the commercially available drug, and can we actually modify one particular CH bonds in that particular drug without touching any of the functional groups in the molecule, right? If that actually happens, then you should be in a position to modify in one step a commercially available drug, and then actually fine-tune their actually bioavailability in the, let's say, in living systems, right? In that way, you will be able to actually, get most actually benefit of actually doing selective functionalization over actually, let's say, synthesize of actually the same compound actually for 20 steps from the scratch. So, and the second most curious actually aspect which we also wanted to actually work in the last few years is actually, can we try to, let's say, convert the waste into chemicals, right? If I'm a chemist, so if I know actually those wastes are actually made up of actually chemicals, and those wastes are actually those materials are actually made up of chemicals starting from the monomers. If that actually happens, then these actually materials can, in principle, actually supposed to be converted back into, let's say, a chemical, right? So, and that's what actually we also look into that. So, to take things actually into perspective, so we actually work on concept and design. We actually largely focus our actually research activity on 3D metal complex and apply them actually in various actually applications, right? So, as I said, actually, there are only three things which I would like to discuss today. So one is actually these are all the biologically active molecules, and can we try to actually take these molecules and functionalize one particular CH bond selectively, let's say, over the other, right? If that actually happens, then we should be in a position to functionalize, let's say, a molecule which are actually quite easy to actually functionalize. Let's say, for example, one particular CH bond on this particular position is actually possible to activate without actually touching this carbon derivatives. Right. So that's the question actually we asked ourselves. And sorry. So the second actually concept which I would like to actually discuss is to see how, let's say, for example, the greenhouse gas emission actually can be, make use as a raw material actually to produce, let's say, useful product. And this is, of course, one of the ideal concept people will expect. Let's say, for example, the CO2 which you actually emit from your transportation, let's say, goes to the atmosphere. Can we actually, let's say, make use of this CO2 and in the presence of water and sunlight, if you could produce, let's say, electricity and the corresponding, let's say, CO2 byproduct, and this byproduct along with the hydrogen which is generated from water can be converted into, let's say, useful products such as, let's say, formic acid. And this formic acid actually can be reduced back into methanol, and this methanol can be used as a renewable fuel. Let's say actually go back to the corresponding car where it actually produces hydrogen, and that actually acts as an energy actually for transportation. And so through this way, you should be in a position to, let's say, recycle the waste into, let's say, useful actually product, right? So, but of course, it's an ideal concept, right? So you need to actually have an efficient actually catalyst to do, every single transformation. For example, CO2 is not a reactive compound, right? It's an inert product, inert actually compound which you actually release over the period of actually time. And water, of course, another actually inert compound which will not actually react with anything. So let's say, for example, how do you actually, let's say, split water into hydrogen and oxygen, right? So that's a big $1 million question, right? So if you could somehow find a catalyst which will actually produce only hydrogen from water, or if you somehow actually, let's say, reduce the CO2 into a useful component such as, let's say, CO, right? Then we know actually the hydrogen and CO can be used as a syngas, and which can be used, let's say, for example, to produce a lot of actually chemicals, right? So with that actually idea in mind, so we thought actually, can we convert CO2 into a formic acid or CO, let's say, by deoxygenation, or you can actually convert it into a, let's say, for example, dimethoxy ether, or you can also, let's say, make a polymer out of actually CO2, or you can convert, let's say, into a methane by hydrogenation actually by completely removing all the oxygen from the CO2. Right, of course, that's a bigger vision. So probably I'm not really sure I will be able to even address some of the challenges. Let's say even in my time in IIT Kanpur, right? But it's a $1 million question. So for sure, actually, it's worth to actually invest our time on these particular bigger issues, right? So the third actually issue which I would like to actually discuss today is the let's say the use of a consumer products. Let's say, for example, any of these actually polymers, right? For me, it's a polymer. Okay, it's a plastics which was actually used by the consumers and largely thrown out actually to the environment, and none can take care of actually this kind of plastics, right? So what it implicates that these non-degradable polymers are actually going to exist on the environment forever, right? If we somehow actually find a way to recycle actually these polymers, then we should be in a position to actually clean our environment, and that's what actually teaches us during this pandemic time, that how air can be clean. Let's say if a human being do not disturb, it actually clean it on its own, right? So it does not actually require a human to, let's say, clean. For example, let's say if you take a Ganga to clean, you have to actually, let's say, invest several million euros to clean, right? So you don't disturb by the human intervention, let's say, then you will actually see the Ganga clean itself, right? So that's what I mean, right? So but that cannot be possible because we, as a human being, are actually quite ambitious. Actually, want to disturb everything and wanted to have a better lifestyle, which means we will eventually actually going to produce a lot of waste. So the only way to actually, let's say, forego is to see how we actually, let's say, take those waste into back into chemicals or to recycle it. Okay, to take things actually one by one, I wanted to actually see actually these pictures, and these pictures that clearly see for you is like a pictures, and for me this is a molecules, right? Let's say if you look at, let's say, drugs or a fuel cell or even actually envelope or even a moon boot, these are all actually made up of molecules, right? If these are actually made up of molecules, and these molecules are made up of what? So these molecules mostly made up of, let's say, noble metals. If this is really true, how these transformations occurs with the help of noble metals. Let's say, for example, a typical transformation occurs starting from the hydrocarbon, which was actually absorbed, which was obtained, let's say, for example, from the oil resources, and that actually hydrocarbons actually converted into, let's say, for example, reactive derivatives, and these reactive derivatives actually converted actually back into an actually second reactive derivatives, and followed by, let's say, nucleophilic or electrophilic substitution, you should be able to actually get the corresponding product formation. So what you do in the process is that every single step which you actually derivatize, you will not actually produce only product, you will also actually produce an equimolar amount, perhaps even more than equimolar amount of the waste, right? If that actually happens, so you will actually produce, let's say, starting from 1 kilogram of hydrocarbon, actually produce 1 kilogram of the product, but then you will also produce 10 kilogram of a waste, right? And those 10 kilogram of a waste, if it is not actually recyclable, it's going to actually harm the environment, right? And that's where actually we ask the questions, can we try to actually see a direct route actually to functionalize the CH bond into a corresponding, let's say, a product? If that actually happens, then we should be in a position to cut down all these three routes. So thereby the reduction of waste is going to be significant, right? If this is really true, how can we actually make the CH bond to be more reactive? We know, or we study actually from the textbook, the CH bonds are most inert actually bonds which we see compared to, let's say, a CX bond, which is actually highly polarized, right? So because of which, so we need to actually have a catalyst which should actually in principle be able to activate the CH bond in a selective manner. So how do you actually define the selectivity? Let's say, for example, if you have an arene, a functionalized arene. So if you have a functionalized arene, so obviously we already started actually differentiate the hydrogen bonds, let's say CH bonds. So ortho CH bonds, meta CH bond, and para CH bonds. And at the same time, if you take, let's say, an alkane, so again, you will actually start to differentiate the CH bonds, let's say a primary terminal sp3 CH bonds and secondary sp3 CH bonds, and the secondary sp3 CH bonds actually can also be biased by electronically, right? So if you could somehow find a way to activate these CH bonds in a selective manner, then in principle, you should be able to, let's say, do this transformation, let's say, from A to B in one-step synthesis, right? But that in principle is going to be very difficult, right? Because your metal catalyst has to at least selectively recognize one particular CH bonds over others, right? But if you really look at nature does so fantastically, right? It actually picks up one particular CH bond and hydroxylate actually, let's say, selectively compared with, let's say, another CH bonds. But we, a human being, even a chemist, do not actually come to actually even closer to the nature's actually achievement. So perhaps actually it's not too far away that actually we are not actually going to achieve that, right? So the key question is that can we actually try to actually put some kind of a linker, and then actually this linker will actually have kind of a tether. Actually, that tether will bring the metal in close proximity to the CH bond. If that actually happens, what you will see, let's say a CH bond will actually interact, especially the CH bond orbital will actually start to interact with the metal, and thereby you induce the CH bond cleavage, or you elongate the CH bond actually, so thereby you cleave the CH bond in a selective manner, okay, compared with others. Or in other words, let me ask a simple question. Let's say, for example, if I actually take benzoic acid, if I take a nitrobenzene, right? If I wanted to make a 3 alkylation, then can I actually make it orthoselective, right? If I take, let's say, a toluene, if I take, let's say, for example, methoxybenzene, can I actually make it more metaselective, right? Because we know that these are all actually ortho-para-selective. When it comes to 3 alkylation, it does not actually go for meta, right? But with the help of metal catalyst, we should actually reverse this particular process. That's what actually I try to mean, right? So again, to convince you further that why 3D metals are important, so you will clearly see the abundance of 3D metals over, let's say, noble metals. So the noble metals on the Earth crust is almost negligible. So which means the process which you develop based on noble metals will exist for another centuries, okay? But the source actually for those processes will not exist forever, right? So that means that you need to look for an alternate resource, and so that's where the opportunity actually comes with the 3D transition metals, where the abundance of these metals on the Earth crust is enormous, right? So in comparison with the noble metals, and that is one of the reasons actually we thought actually to work with the 3D transition metals, and of course it reflects on the price, and you actually see on the left side. So where the per gram with respect to dollar of iridium, palladium, rhodium, and platinum is almost negligible in comparison, let's say, with the cobalt, for example, right? So the cobalt price is so cheap that you can even actually buy several hundred grams, in place of, let's say, 1 gram of actually these noble metals. So CH bond functionalization is not actually something I invent. It is already there, and as you can clearly see that actually over the period of last decade, the number of publications which actually got increased tremendously, especially for actually CH bond transformations using noble metals, right? But as you can also see, how actually these numbers will actually vary with respect to different metals. You clearly see the palladium lead the role, and then actually rhodium, ruthenium, are also actually following the same trend. But as you can clearly see, actually from 2014 onwards, so the emergence of 3D transition metals actually started to actually go up, and I can clearly see it goes, let's say, from 10 publications with respect to cobalt actually to go to, let's say, closer to 200 publications, which clearly indicate that there is a lot of interest actually by the people using actually these metals actually for CH bond consolidation. So I chose to actually work with cobalt. Why? There is a reason behind it, because again, I want to actually go back to textbook and see their actually fundamental properties, right? So cobalt D9 system easily removable like 1 electron, so which means you can oxidize 1 electron easily. Or you can also, cobalt is a very small in size compared with, let's say, other group 9 metals such as iridium and rhodium. So which means the fundamental property of this particular metal should be different compared with, let's say, rhodium and iridium. And cobalt smaller in size and high valence oxidation state, obviously it is going to have a different electronegativity, and cobalt again smaller in size and high oxidation state actually have a very hot actually in nature compared to, let's say, soft rhodium 3 and iridium 3, right? So again, I do not actually want to actually discuss more actually about the advantages and disadvantages. The only disadvantages actually people believe over the period of last, let's say, 50 years is that the cobalt going to be, or the many metal catalysts actually going to be very active only at the low valence oxidation state, right? So because when it is at low valence oxidation state, we learned actually from the textbook, and we teach actually to our students that the low valent actually metal complex will go for oxidative addition, right? If that is really true, if you take, let's say, a cobalt 0, we'll actually go for oxidative addition with the CH bond, which actually liberates, let's say, cobalt 2 species, right? Rather than, let's say, you start with the cobalt 3, which actually goes for oxidative addition, which is, in my opinion, impossible, right? So that is why people trust actually that you need to have a reducing agent even if you start with the cobalt in high valence oxidation state. and thereby, of course, you produce a lot of stoichiometric amount of waste, right? And it is not actually going to be any more sustainable. So this is when we thought, can we actually try to actually use, let's say, high valent cobalt and try to do a process at the high valent oxidation state itself, instead of actually reducing into a low valent oxidation state and then actually do a transformation, right? So again, before we actually go into detail, we want to actually study, the fundamental difference between, let's say, a cobalt cycle versus rhodo cycle, and how, this fundamental difference is going to have an impact on the, let's say, for example, catalysis. Okay, so this is the two different crystal structure isolated in the literature. So you clearly see there is a cobalt carbon bond versus, let's say, a rhodium carbon bond. And what we will clearly see, the cobalt carbon bond distance is about 1.9 compared to, let's say, rhodium carbon distance is about 2.0. So which indicates that the distance between the rhodium and the carbon is longer, and the distance between the cobalt and the carbon is shorter. What it implies that the cobalt carbon bond is shorter, because of which the nucleophilicity of the carbon attached with the metal such as cobalt, for example, is going to enhance significantly compared to, let's say, a carbon which is attached with rhodium, right? So quite similar like what we observe with the Grignard reagent, right? You take an RNGX where the R have a significant nucleophilicity compared to, let's say, other metallic reagent. Okay, in the same way, the cobalt will, in principle, should actually have a different reactivity, or perhaps it is unique reactivity compared to rhodium and iridium, right? So this is where our starting point. So, and I will actually take with 2 or 3 examples and convince you that these fundamental properties indeed actually have an impact on the catalysis. So, let's say one example we want to actually see is, can we actually do an atomeconomical transformations where everything we use as a reagent is catalytic except the reactant, and all the reactant which you use in the left hand side should actually reflect on the right hand side so that you do not actually produce any waste, right? And this is one of the examples which I would like to show, where you actually start with the quinoline oxide and treat with an alkyne. So you would expect, let's say, for example, this oxygen directed cobalt actually come closer to this CH bond, activate this CH bond, and you form a metallocycle. Alkyne comes, bind, insert, and then actually goes for a proto-demethylation. You end up getting the corresponding alkylation product. But there is a question here, right? If you look at the acidity of this C2CH bond versus, let's say, CH-CH bond, the C2CH bond are actually more favorable because it's more acidic compared to, let's say, CH-CH bond. But if you look at, let's say, the metallocycle which actually forms with the C2CH bond versus, let's say, C8CH bond, so the metallocycle forms in this particular case is about 5-membered metallocycle compared to, let's say, in this case, is about 4-membered metallocycle. And we know these 5-membered metallocycles are actually thermodynamically more favored compared to the 4-membered metallocycle. And that's why we feel that it's going to actually favor on the C8 position rather than the C2 position, right? So surprisingly, we do not actually end up in the alkylation product. We rather end up in actually getting the corresponding, let's say, beta-aryl ketones, alpha-aryl ketones. So what it actually tells you that the oxygen which is initially bound with the nitrogen is now actually coming to the carbon, and it is not actually anymore having a bond with the nitrogen, for example, right? So you have an alkyne, stem is here, you have an oxygen which is actually attached initially with the nitrogen, and it comes to the carbon. So which means all the atoms which actually on the left side are actually going to be intact on the right side. It's a 100% atom efficiency reactions. So, and we have optimized it, and that's optimized reaction conditions. And so to show that the reaction indeed actually have a wide scope, so there are actually plenty of quinoline-based compounds can be used, and it can be selectively alkylated actually on the C8 position, okay, rather than the C2 position. In addition to that, if you look at, let's say, an electronically biased alkyne such as an unsymmetrical alkyne, so you will actually see a selective functionalization where the alkyl group always comes on this particular carbon, alpha to this particular carbon, rather than the aryl group. And that is the same case, let's say, if you go from methyl to ethyl and then also in the long chain alkyl, it always actually comes to only this particular position rather than actually attached directly to the corresponding carbonyl carbon, right? So we do not understand actually why such a reduced selectivity occurs. If so, how do you explain that? So first of all, this was actually explained with the help of, let's say, Richard, who has actually done a EFT calculation in detail for this particular one. So he has shown clearly that this conjugation of phenyl olefin with a double bond of the quinoline plays a crucial role, and compared with, let's say, for example, with methyl on this particular terminal position, and that's one of the reasons actually this particular intermediate is more stable compared with, let's say, another intermediate, and thereby you actually transfer this oxygen actually to this particular carbon and then get the selective product in the case of unsymmetrical alkyne. All right. So the second question comes. So when we actually do the reaction, let's say, for example, in this particular example, So where with cobalt we got about 70% yield, with rhodium and iridium we got about 15% and 0% yield, which clearly indicates to me that there is something else exactly going on. So, I mean, when we actually do the DFT calculations with, let's say, ligand to metal charge transfer, what we found is that the electron-rich alkyne with metal, with respect to, let's say, cobalt, it is actually going to have a huge impact, let's say, compared to rhodium. It does not actually have any impact on the ligand to metal actually charge transfer. I mean, that's one of the reasons actually we get a pretty high yield in terms of, let's say, electron-rich alkyne compared to, let's say, electron-poor alkyne. Right. The second transformation which I would like to show, again a green transformation, so where we do not actually produce any waste except water, is, let's say, can we selectively do a CH bond alylation, okay, on this particular position, right? So what we actually established in the previous case is true. We should be able to actually make the CH selective cyclometallation followed by alkene insertion, and then actually, let's say, beta hydroxy elimination. This should actually give the corresponding alylation product. And for your information, beta hydroxy elimination is not an established textbook reaction, right? So what we actually know is the beta hydride elimination, which is very well established over the centuries as an elementary organometallic reactions. And so thereby this beta hydride elimination occurs. If that actually happens, so you will end up in getting the corresponding alylation product. So if that actually happens with rhodium, then you will also get the similar product like with the cobalt, right? But surprisingly, for our actually observations, so what we actually found in the case of cobalt, under the similar reaction conditions, except actually metal is changed, right? So on the right side, what we actually see the selective alylation product. On the left side, what we actually see the selective beta alkyl ketone product, right? So which clearly indicates to me that actually there is a two different actually fundamental reaction occurs, okay, in the catalytic cycle, and due to which, so on the case of cobalt, you get the selective beta hydroxy elimination, and in the case of, let's say, rhodium, you get a selective beta hydride elimination. So how do you explain that? Let's say, for example, assuming that you are actually in this particular scenario after the initial cyclometallation followed by alkene insertion between the metal and the carbon, you will at least get into this kind of a scenario. On the left side, where rhodium is bigger in size and high valence oxidation state, and it's going to be a very soft in nature, right? So which means it's preferentially take the soft hydride rather than the hydroxy and goes for, let's say, a beta hydride elimination compared to, let's say, cobalt at a high valence oxidation state, very small in size, going to be very hard in nature, and it preferentially takes, let's say, hydroxy over actually hydride. If that actually happens, then cobalt will give a beta hydroxy elimination. Again, it is not a textbook actually reaction. It is never actually established well in terms of, let's say, organometallic chemistry, right? So what we actually try to show and prove is that it is possible indeed to go for a beta hydroxy elimination provided if your metal is hard in nature, compared to, let's say, rhodium, which is actually very soft and that cannot actually go for a beta hydroxy elimination. And this is one of the important contributions in terms of, let's say, fundamental understanding of organometallic reactions. So indeed, it works. It gives a plenty of scope. Let's say with cobalt, we only get a alylation product, and when it comes to rhodium, we only get, let's say, a beta alkyl ketone product. So that clearly indicates that it is actually metal-based, and rather than, let's say, extension of, let's say, rhodium chemistry with cobalt. It is not actually extension of rhodium chemistry with cobalt. Cobalt itself has its own unique reactivity compared to, let's say, other group 9 metals. Okay, so of course, it actually works with the HSAB principle, where the hard goes with hard and the soft actually goes with soft, and that clearly indicates actually in this particular example. So so to prove that actually this concept is indeed actually applicable to several other examples, so we have also actually shown that the selective alkylation is actually possible provided if you have such kind of an organometallic species. And of course, everything has to be proved, okay, because nothing is new, nothing is known actually in terms of high valence chemistry. It's all actually started in 2030, right? Before that, there is absolutely no mechanistic investigations that's actually done with respect to, let's say, high valence cobalt, especially with the C cobalt chemistry, right? So we try to actually study the mechanism of that particular reactions, and we isolate the interactive intermediate which is involved in the catalytic cycle. And that's the case of section of the 7-membered intermediate, and before it actually goes for proto-demethylation to give the corresponding alkylation product, right? So to take it further, the beta hydroxy elimination in principle cobalt favors. So instead of an allyl alcohol, we take a propanol alcohol, and this propanol alcohol again preferentially takes the hydroxy group which is in syn position to the cobalt, and goes for a beta hydroxy elimination and gives the corresponding allene as a product. Again, tetrasubstituted allenes are not easy to synthesize. Or in other words, you can also actually see, I mean, let's say, for example, such kind of an intermediate which involved in the catalytic cycle. And so that will actually goes for the corresponding product, I mean, before before it goes to the corresponding product. That's the intermediate which we have time under the same reaction conditions, but in stoichiometric manner. So, but the moment you change the steric of this R1 and R2, what we'll actually see, instead of, let's say, beta hydroxy elimination, there is a free rotation of the hydrogen and the hydroxyl group, and thereby you will end up in getting the selective beta hydroxy elimination. In this case, you are actually getting the corresponding alkylation product over an alinylation product. Okay, so under the same reaction conditions, just by steric, as well as, let's say, hard or actually soft nature, you will end up in getting the two different actually products. So all it indicates that in these particular transformations, there is absolutely no actually waste. Everything which we use other than the reactants are actually catalytic, which means the reaction is actually more greener compared with, let's say, traditional organic chemistry transformations. So far whatever I have shown to you is only the CsP2 H bond functionalization, right? So there is a reason actually behind actually we start to work with the CsP2 H bond functionalization, because the CsP3 H bond functionalization is not actually easy to activate, right? If this is really true, right? But by looking at this data, for example, the bond dissociation energy of actually the CH3 H bond over, let's say, a CH bond. If we take, let's say, for example, butane, let's say, versus, for example, benzene. Butane is, let's say, 395 versus, let's say, 431. And if you look at, let's say, methane versus, let's say, benzene, both are actually having the same bond dissociation energy, right? If I am able to activate, let's say, benzene, then I should be able to activate, let's say, for example, methane also, right? But that's not true, right? Because it is not only the bond dissociation energy that matters, it is also the pi orbital of the sp2ch bond actually going to have a significant role to bring the metal actually in close proximity to the CH bond, compared with, let's say, an sp3 CH bond, where you do not actually have the pi orbital. In addition to that, the sigma star orbital of the sp3 CH bonds, antibonding sigma star orbitals of the sp3 CH bonds are very high in energy, so it is not easy for the metal to access, and that's one of the reasons sp3 CH bonds are difficult to activate, right? So to take it further, so we take this particular example and we see if the metal somehow actually coordinate to the nitrogen, right? Which in principle should be possible, because nitrogen-based donor ligands are actually known with cobalt or any other metal, right? So if that actually happens, I'm actually taking this benzenic CH bond closer to the corresponding cobalt, and thereby activate this particular CH bond and get the corresponding metallocycle, and that actually react with an electrophile and produce the corresponding product, again to see if that actually happens in an atomical manner, right? So that means everything has to be catalytic. So I do not actually want to go too much into an optimization. That's an optimized condition. We take the corresponding 8-methylquinone and treat with an alkyne, and what we actually see is the corresponding alkyne insert in the CH bond and produces selective olefins at the C8 portion of the corresponding quinone, right? If that actually happens, you will selectively actually form the corresponding alynation of a quinone at the C8 portion, right? So the reaction is in general actually applicable to large variety of alkynes, and it gives only the CH inserted actually alkynated product and does not actually produce any waste. It's a 100% atomic efficient reaction, right? But then you need to understand actually how this reaction works, right? So does it actually going to work in a similar way as an sp2ch bond, or it's going to have a different mechanism, right? So let's say the CP star monomer will actually have the possibility of actually forming the corresponding kappa 2 coordinated carboxylate bind to the cobalt, and that in principle replace the ligand, for example in this case substrate, actually with one of the oxygen of the kappa 2 carboxylate to have the corresponding L ligand bind to the cobalt, and thereby you bring the corresponding CH bond close proximity to the cobalt. Now there is a two different scenario occurs, right? How does the CH bond actually going to be deprotonated, right? There are actually two different scenarios. One, where the carboxylate bind to the cobalt directly to the metal, and the second one, the carboxylate sitting outside the coordination sphere, and that will actually comes and actually picks up the CH bond inside the coordination sphere, right? So how do you prove that? So it's very difficult to prove such kind of a scenario. One way to prove is actually to do a kinetics. So if you add, let's say, 10 mole% each of carboxylate every 10 minutes, right? Then you will actually see, the conversion of a 10 mole%, 20 mole%, 30 mole%, 40 mole%, you will actually clearly see by adding more carboxylate source, your kinetics will actually go faster. If that actually happens, you will clearly see that it is an external base assisted actually deprotonation rather than internal base assisted deprotonation, right? So, but as I said, we do not actually have much patience at that time because it was actually a hot topic. So we get a help of actually Richard, who tried to actually help us on understanding this particular deprotonation. And it clearly indicates it from the calculations saying that, so the carboxylate which actually comes from outside the coordination sphere going to actually have a lower in energy compared to, let's say, copper oxide bind with the metal directly for the possibility of intramolecular CH deprotonation. So that's again clearly tells that the mechanism which operates in the sp2CH bond is quite differently compared with an sp3CH bond. That's again another actually very good contribution from our group to the society, saying that actually it is not actually the same mechanism which operates compared with sp2 as well as in sp3. Right, so to take it further, let's say, for example, if that actually happens, you will form the corresponding cobalt cycle, alkyne comes, insert actually between the metal and the carbon in a serious selective manner, and then you produce the subnumbered alkylyl intermediate, and that subsequently goes for a proto-demethylation to regenerate the catalyst. So again, 100% atom efficient reaction, there is absolutely no waste product formation. Okay, so the question comes again, right? The question that we keep asking us, I mean, can we actually make it further? Can we actually try to improve the activity actually further? Right. So if you look at the 8-methylphenolene, it is a benzylic sp3CH bonds. Can we actually try to use an inactivated sp3CH bond? If so, then we should actually get a more useful actually transformation rather than, let's say, simple 8-methylphenolene. Then it is a substrate specific, right? So we thought actually taking this particular aliphatic carboxylic acid, which can be easily attached with, let's say, nitrogen-based bidirected ligand. And this nitrogen-based bidirected ligand take the metal, coordinate to the metal, bring the metal close proximity to the CH bond, activate the CH bond, you will actually get the corresponding cyclometallation, and the small molecules such as CO should in principle insert, followed by reductive elimination gives the corresponding carbonylation product, let's say, in one part synthesis, right? So if that actually happens, you can start with the corresponding carboxylic acid, let's say aliphatic carboxylic acid, and you end up getting the corresponding succinylate derivatives in just one step without actually having any other actually side product. But then, as I said actually in the past with the CP chemistry, everything we use is catalytic. There is nothing is actually stoichiometric. And here is a concern actually comes. So we use 10 mole % of a cobalt, and we use, let's say, 20 mole % of a carboxylate as a base to deprotonate CH bond. But then we have to use an additional 3 equivalent of a silver carbonate, which to me is a lot, right? If you really want to actually do this particular reaction in 1 kilogram scale, for 1 kilogram starting material converted into 1 kilogram product, you have to actually produce 3 kilogram of at least silver residue as the side product, right? If this silver residue actually going to have impact on the environment, then I need to worry about actually the silver residues, right? So that's when we thought, let's say, for example, so we take the silver residue comes out of the reaction, and then treat with nitric acid, we form the corresponding silver nitrate, and this silver nitrate is converted back into a corresponding silver carbonate. Okay, that's what actually we use in the reaction mixture, right? And this recycled silver carbonate again taken and perform the reaction, and with the recycled silver carbonate, we were still able to get the corresponding product, which means even if we use the silver carbonate in excess, and this can be recycled, and then this can be actually further used actually for the same transformation, right? So we again take it actually further. So CO is reactive gas. Of course, it can insert actually with the metal and the carbon. We study or we teach actually to the MSc students, right? But if you take, let's say, a metal carbon agrometallic species and treat with the CO2, there is nothing is going to happen, right? So, or in other words, CO is more reactive compared to the CO2, right? So, but if you look at actually CO2 is abundant. We actually emit CO2 on an everyday basis. Can we actually try to use the CO2? Again, the bigger question I asked at the beginning, I'm coming back to the same question now, right? So, can we make use of CO2 as a raw material? Okay, and then convert it into a CO gas. If that actually happens, we form the CO in situ, and in situ we form the corresponding agrometallic species, and this will actually use the corresponding product, okay, without actually much trouble, right? Of course, the inspiration actually comes from the corresponding, industry which I have actually exposed myself in Germany. Yeah.
Sir.
Yes, sir.
We are sorry to disturb you. We are running short of time.
Just
a few questions.
Yeah, just 5 minutes and then I will done.
Okay. Thank you.
Yeah. So I have exposed to an industry in Germany. So where you will see yourself actually this industry. There are 130 companies in this particular industry, right? So the pipeline which you actually see through this picture clearly indicates to you that the side product which actually comes from one company actually goes as a raw material to another product. If that actually happens, then can I actually, let's say, produce a gas, a small molecule from one particular reactor, and then I can taken this small molecule into a second reactor and produce the corresponding product. If that actually happens, then I produce only a product which is otherwise actually not possible with the one-pot reaction, right? So we take a CO2 and produce a CO gas with the selective conditions, and that particular CO gas can be trapped with the organometallic species, which is generated in situ to form the corresponding carbonyl derivatives. Again, actually starting from CO2, right? So we can actually make, let's say, a variety of benzamide thalamide or a saccharin, for example. We can also actually make, let's say, a variety of succinimide derivatives, actually starting from the CO2 gas, to show it to you, to convince you that indeed actually these applications are very useful. So we take, let's say, a commercially available telmisartan, which you can actually buy it from the supermarket or you can buy it from the medical shop, and take this actually compound, attach it to it, and actually produce a CO gas from the CO2 in situ, and trap the CO gas coupled with, let's say, organometallic species in situ it forms, and what you actually produce is the corresponding carboxylic acid after the hydrolysis, right? So you start with the corresponding carboxylic acid, which is nothing but the telmisartan, and you selectively functionalize one particular CH bond and produce, let's say, 13C labeled CO2H. 2 carboxylic acid, one is the 13, and 12 C12 carbon, another one is the C13 carbon, right? It is not actually with only one pharmaceutical drug you can do it. You can also actually do it, let's say, for another pharmaceutical drug, which is again $1 million drug. So fibrosis, for example, you take this particular compound, attach it to the, add actually your in situ form the CO gas actually coming from the CO2, and then actually make the corresponding, let's say, succinimide derivatives. Actually, after that, you actually hydrolysis get the corresponding bis-carboxylic acid actually coming from the drug directly from the market, right? That's what actually I mean. So you actually take a material which is available commercially, okay, and can you actually convert that into a selective, one particular CH bond over other, then you use out actually a lot of the chemical transformation. So that actually culminates a lot of our efforts actually in this particular area. So over the last 5 years, I will not actually take much in detail. So I finished actually my talk with last one particular question, right? So which is nothing but the polymer, right? So we all actually know how polymer impacted on our actually case, and these polymers are indeed actually going to have an impact widely in terms of, let's say, our day-to-day life, and that you can be clearly see. So another thing actually is the waste recycling, because actually we produce a lot of waste after the consumer use, and that is one of the reasons actually we need to worry about it. So one of the way to actually do this, let's say, can we convert this polymer into a monomer, okay, through hydrogenolysis? If so, can we actually use cobalt as a catalyst, right? So that's where actually we try to actually develop a lot of actually well-defined cobalt complex, and these cobalt complex were used as a catalyst. For example, direct conversion of CO2 to methanol is very difficult process, but then you can convert the CO2 into a corresponding carbonate, and this carbonate can be converted into a corresponding alcohol and methanol. Okay, in that way you can directly do the methanol production along with, let's say, monomer, right? At the same time, you can also, let's say, produce the cobalt catalyst effectively to produce the corresponding methanol as well as the monomer, right? So we buy the commercially available polymer, we expose to our reaction conditions, and what we actually form is a corresponding monomer, okay, in a very good yield, okay. And then we actually try to see, can we try to really apply in a real-time base. We take a CD disc, we cut the CD disc into small pieces, we take the small CD disc into an autoclave and do the hydrogenolysis. When we actually do the hydrogenolysis, what we actually get is the corresponding monomer, which is nothing but the bisphenol, which is actually the monomer of polycarbonate that is available on the CD disc, right? So that is clearly indicates that it's a waste converted back into a corresponding monomer, okay, without actually producing any other waste, right? That means you can take, let's say, a waste which is actually thrown out on the environment, take it back, do the hydrolysis, and get back to your actually monomer from the polymer. So thereby you will recycle most of the waste which is actually thrown out after the consumer use, right? So I do not actually have much time actually to show, other activities which actually goes on in my lab. I directly actually acknowledge the people who involved in my work is actually none other than actually my students, and without actually their hard work and effort, it's simply not possible actually for me to achieve this. And I owe a lot of actually respect actually to them actually for their hard work in my lab, right? And of course actually I'm thankful to funding agencies, and I also actually very happy to answer actually if there is any questions. Thank you very much, and thank you, St. Joseph's actually for giving me this opportunity to showcase our results. Thank you once again. Hello.
Informative and very useful talk on the sustainability We are very much thankful to you, sir, for accepting our invitation as well as delivering a very wonderful talk on this topic. And you have done 200% justice to the topic you have assigned to you. We are very thankful to you, sir. On behalf of the participants, we have a few questions. Let me ask you, sir. The first question is, explain why 3D transition complexes are better sustainable catalysts than 4D and 5D.
Yeah. So, I mean, as I said in my talk itself, that the 3D transmitters are actually available large on their crest. I mean, let's say compared with, let's say, 4D and 5D, in particular the noble metals. Okay, and because of which the 3D transmitters are actually going to have an impact in the next century compared to, let's say, 4D and 5D transmitters. It is mostly purely based on the abundance and not actually based on anything else.
Thank you, sir. Can nano catalyst be used for wastewater treatment?
Certainly, it is possible. Okay, people actually also develop a catalyst actually based on nanomaterials or metals actually based on not a catalyst. But certainly, I am not expert on that particular area. I mean, it is not appropriate for me to comment on that.
Which catalyst is more suitable for plastic recycling?
So, as I said, any catalyst which is actually widely available on Earth crust, even after the catalytic processes, if we throw those catalysts on the air, it should actually degrade. If that actually happens, if the catalyst is not plastic, then it should be possible actually to use those catalysts actually for, let's say, waste recycling.
Thank you, sir. We have few more questions. Due to lack of time, we send all the questions to your mail and we will get clarification. Thank you, sir. Thank you once again for your acceptance and for doing justice to your alma mater. Thank you so much, sir.
Thank you so much. And I also owe a lot of respect to the teachers actually from St. Joseph's. I have a lot of actually respect to them. I've learned actually quite a lot actually from them, and I continue to actually have that respect actually to those teachers as well as actually St. Joseph's. Thank you very much actually for the opportunity you have given to me. Thank you.
Thank you. Welcome, sir. Dear participants, feedback form will be available in the chat box. Give your feedback after the second session is over. For the kind attention of participants, feedback form will be available in the chat box. Give your feedback after the second session is over. The second session of today's seminar is construction of stable duplex by acyclic nucleic acids by Dr. S. Chandrasekhar from China, Shenzhen University. Before we start the session, I request Dr. A. Stella Salini, Assistant Professor of St. Joseph's College, to introduce today's resource person. Welcome you, ma'am.
Distinguished delegates, esteemed professors and participants, good morning to all of you. I am Dr. Stella Shalini, Assistant Professor. I deem it a great privilege and honor to introduce this session resource person, Dr. S. Chandrasekhar, to you. About his educational qualifications and research experience, he did his bachelor's degree in chemistry from Government Arts College, Ooty. Then he completed his master's degree in chemistry from St. Joseph's College. He was a brilliant and hardworking student, and I am very proud that he was the student of mine. Because of his hard work and determination, he has qualified in the CSIR exam with JRF, and also he qualified in the GATE examination. Then he entered in the Indian Institute of Technology, Chennai as a project assistant. There he completed his PhD degree also. His area of specialization is in synthetic organic chemistry, and he has published a number of research articles in various reputed national as well as international journals, especially in this area of synthetic organic chemistry. And about his awards and fellowships, he has received fellowships like Junior Research Fellowship, Senior Research Fellowship from UGC. Apart from that, he has also received Institute Postdoctoral Research Fellow Award from Indian Institute of Technology, Chennai. And currently, he is working as a postdoctoral research fellow in the Institute for Advanced Study, Shenzhen University, China. Such an eminent person with good academic record and rich research experience is going to enlighten us with a talk on construction of stable duplex by acyclic nucleic acids. So on behalf of all of you and on my own behalf, I wholeheartedly welcome Dr. S. Chandrasekhar. Thank you so much. Over to Dr. Chandrasekhar.
Sir, now are you getting? Okay, thank you, sir. Okay. Thank you very much, madam, for your kind introductions. Thank you for everyone attending the presentations. I would like to thank department and other faculties for giving the good opportunity, particularly Professor Jodi is given the good opportunity for presenting the my St. Joseph College. Okay, I will start for my presentation. Construction of stable duplex formation by acyclic threonine nucleic acid. My talk was arranged in the following manner. Introduction part, I will talk about the nucleic acid and DNA backbones. Why you need for the artificial DNA. Then further, I will discuss the synthesis of the threonine based nucleotides and applications using the ruthenium complex and the graphene oxides, and followed by conclusion. First of all, what's a nucleic acid? We want to know first, nucleic acids are the biopolymer or large biomolecules that make up all the living things. Nucleic acid that contains hydrogen, oxygen, nitrogen, carbon, or phosphorus. We know all of the DNA and RNA as nucleic acid that contain the genetic instruction for the development and the function of living things. What's the difference between the DNA and RNA? Only difference between the sugar moieties. One is deoxyribose sugar moiety and ribose sugars. The main role of the DNA is cell is long-term storage in the cell. So DNA molecules consist of the two biopolymers. One is 3' and 5'. That 5' and 3' are made up with the polynucleotides. What's the polynucleotides? This polynucleotides is made from the simple monomer we call the nucleotides. This polynucleotides are joined by the hydrogen bond. So what's the nucleotides? Nucleotides are phosphate and sugar and a nitrogen base. 3 parts contain the nucleotides. Nucleotides, the nitrogen base contain maybe adenine, thymine, and guanine and cytosines. And other sugars and phosphate I will discuss next slides. One second, sorry, it's not present. The PowerPoint is not coming. So in this slide, sir, சொல்லுங்க sir. Hello. Yeah. Okay. Now it's okay. Okay, sir. Okay. Thank you. Yeah, it's fine. Yeah, thank you, sir. Thank you very much. So in this slide, I shown some of the phosphate derivatives. I shown this the DNA phosphate derivatives. It is the triose nucleic acid derivatives, and this triose phosphonucleic acid derivatives, and the deoxyphosphonoucleic acid. All the phosphorus derivative nucleic acid are limited by the metabolic stability, lack of orthogonality, and the toxicity. So we need for the alternative. So they started for the artificial nucleic acid, that is called the xenonucleic acid. I shown the slides, some of the nucleic acid for the artificial nucleic acid. I shown for the example of the DNA, and a peptide nucleic acid, and a glycol nucleic acid, and a serial nucleic acid, and a threonal nucleic acid. You compare this, all the artificial nucleic acid, threonal nucleic acid was compared to other nucleic acid properties was good. Because of this second question, methyl group is present. This methyl group is playing the very important role compared to the other nucleic acids. Particularly the threonucleic acid, some have some special properties, that is for the duplex formation involve the complementary pairing and the anti-parent patient like DNA and RNA. It is backbone for the very flexible, and the thermal stability also compared to the other nucleic acid, DNA and PNA, GNA and threonol, some other phosphate derivatives also compared to this one. Threonal nucleic acid was very good properties and very stable. So with this introduction, I move on for my work. I synthesis for the threonol based nucleotides, we need for the two starting material. One is amine and one is acid. So I started for this acid preparation using for the thymine and potassium carbonate and the methyl bromoacid. We got corresponding for thymine one ester. The ester was further hydrolyzed using for the sodium hydroxide. We got corresponding thymine one acetic acid. This amine compound was synthesized from the threonol. The threonol was first amine was produced using for the ethyl trifluoroacetate. We got corresponding this product 80% of yield. After that, we exactly whatever primary and secondary, we selectively produced for the primary alcohol using for the DMT chloride and the DEPA and the DMP. We got corresponding alcohol product DMP compound. Further, this amine deproduction was used for the aqueous ammonia and the ethanol. We got corresponding this compound 70% of yield. We taken this amine compound and acid compound, we coupled using for the DMTMM and the triethylamine and the DMM. We got corresponding 70% of coupled product. After this product, we converted the nucleotides using for the 2-cyanoethyl diacetyl chlorophosphonolates using triethylamine. We got corresponding 80% of yield. This molecule was confirmed by the proton NMR spectroscopy. These aliphatic 15 protons, these 12 protons, aliphatic methyl and this methyl group, we confirmed by the 15 protons, and DMT 6 protons, we was confirmed by the around 3.6, and remaining is alified the aromatic protons or almost 14 protons we confirmed. With this confirmation, we went for the other confirmation, carbon spectroscopy. We confirmed by the carbon spectroscopy also. Further, this phosphorus was confirmed by the phosphorus 31 spectroscopy. Around is coming for the 2 peaks, is coupling the 2 peaks. After synthesizing for the L-threonol, we started for the D-threonol compound. D-threonol compound is not commercially available. So we started for the D-threonine using, first we started for the D-threonine amine production using for the CbZ chloride in the potassium carbonate, the sodium bicarbonate, we got corresponding the CbZ chloride amine production. After amine production, we further acid was reduced for the using for the BDS and THF solvent, we got a corresponding alcohol 80% of PV. After the alcohol, using for the amine alcohol production, using for the DMT chloride dry pruning, we got corresponding the primary alcohol production. After alcohol production, we amine D production using for the palladium carbon and methanol and ethyl acetate, we got corresponding the amine compound, this is called the D compound, D-threonol compound. After D-threonol compound, we coupled for the amine and all acid compound using for the DMTMM and the triethylamine, we got corresponding the coupled compound. After coupled compound, we convert to the amide using the phosphonamides. We synthesizing for the two threonol compound L and D. After that, we focused for the adenine phosphonamide synthesis using the we need synthesis for the adenine 1 acetic acid. Started for the adenine compound using sodium nitrate, benzyl bromoacetate. We got for the corresponding ester compound. After ester, we product for the amine using for the benzyl chloride. We got corresponding 70%. After ester, we further reduced for the benzyl group using palladium carbon and hydrogen. We got corresponding the adenine 1 acetic acid 60% of value. Once getting the acid, we coupled it with the same like a amine compound. It is L compound. We got corresponding the amide compound, the adenine amide compound. Further, this nucleotide was synthesized using for the phosphonamide compounds. This compound also we confirmed by the proton NMR spectroscopy and the carbon and the phosphorus. After synthesizing this compound, we designed for the some sequence. We synthesized like more than 25 sequence. I shown for only 4 sequence. It is for the natural sequence T1 and A1. It is for the thymine compound. It is for the adenine compound. And you modified for the artificial compound, like same you taken for the threonol like a thymine compound sequence. You modified at the 6th position. You taken the same like adenine compound. You modified 6th position. It is for the DNA synthesizer. We can synthesize at a time more than 10 compound, and you can use for only polar solvent. So once you started for the synthesizing, we used for a different polar solvent, DMF, DCM, DM also every solvent. We observed only for the DCM case little bit around 70% of purity. You can go for the acetyl case, we got for the around more than 96% of purity. So when synthesizing this compound, we need for the 4 step. So it is for the sequencing. I shown for the some figures where I modified this molecule. It is for the natural DNA molecule. We modified at the 6th position. It is for the odd molecule, modified positions. See, once we start for the nucleotide synthesis, we need for the 4 steps. One is detilations, that is called the DMT, removal of DMT. Once start you take the nucleotides, remove the DMT. After DMT, you can couple with some same molecule. After coupling, you can oxidize the phosphorus, we get the phosphate. Then phosphate, again, you can go for the capping, we get corresponding compound. Then further remaining molecule will go for the continuum next cycle. So once you synthesize the compound, we started for the purification using for the HPLC, used for the reverse phase column, and is used solvent as the acetonitrile and water 95:5. So once you confirm the HPLC, we submitted for the mass spectroscopy. When we submit the like artificial nucleic acid modified sequencing, we submitted the mass spectroscopy. We observed first 6 molecules, first nucleotides as a mass spectroscopy around 1788. Remaining like 5 nucleotides was observed like 1438. There is coming the one more fragmentation. So with this confirmation, we started for the applications. So we started for the simple, you take the two molecules and take the two sequence. One is the T11 and A11. You will record for the fluorescence studies. There is no fluorescence active. So we need for the some metal catalyst. So we started for the metal catalyst. So first application we used for the synthesis of the compound. We started for the metal preparation, metal complex preparation. Then second application, instead of metal complex, we used for the graphene oxide. So first application, that the metal complex ruthenium pen DBZ complex commercially is not available. So we want to synthesis this compound. We started for the ruthenium chloride. We started ruthenium chloride in 110 phenolphthalein and DMF solvent and lithium chloride. We got corresponding the ruthenium chloride compound. Further, you treated with the phenolphthalein oxide and ethanol water. We got corresponding the phenolphthalein oxide and ruthenium complex. Further, this complex was racemic complex. Further, we want a resolution. So using for the sodium arsenic protein, the sodium arsenic protein also not commercially available. So we synthesized from the D-tartaric acid. When treated with the D-tartaric acid, sodium hydroxide, arsenic trioxide, and water and reflux, we got corresponding the white crystal as a arsenic complex. This was confirmed with the CD spectroscopy. Once confirmed that the CD spectroscopy of this chiral complex, then you used for the resolution, we got corresponding the chiral compound. After chiral compound, you treated with the 1,2 diaminobenzene, we got corresponding the DBZ complex. This pen oxide was synthesized from the 110 phenolphthalein using KBr and concentration, the concentrated sulfuric acid and CONHNO3, we got corresponding the pen oxide. After synthesis in this complex, we used for the, we've taken this two sequences, T11 and A11 with this complex. When using this complex, means only you record the T1 and A1, there is no fluorescence active. So we taken with this complex, we recorded for the natural DNA molecules. There is no selective metal reduction, no selective for the metal reductions. Only for the calcium and cadmium also almost coming for the all the metals coming in equal positions. When go for the artificial modified nucleotides, particularly the mercury ions was selected, particularly selective reduction for the mercury. Other metals were very less. Other metals are coming for the less than 500 intensity. So with this one, we started for the how much the mercury was particularly we can select for the using this sequence. So we started for the sequence by showing here simple TA molecules. TA molecule means whatever trigonal molecule modified sequence. We recorded for the fluorescence. We observed almost 100 intensity. When go for the TA and A1, almost coming for the 200 or like less than 300. So you started for the 1 equivalent mercury and 2 equivalent, 10 equivalent. Almost when used for the 10 equivalent, like a 10 equivalent, this was reduced like a 700 to almost 800. Because I did not show this only simple complex with this complex, because it's coming the around 3000 intensity. I did not show for this PPT. So particularly our whatever modified trigonal nucleic acid, very selective for the mercury reductions. So we used for the emission spectra using for the around excitation 380, using for the phosphate buffer solutions. So next application we started for the using for the graphene oxide. This graphene oxide method was synthesized from the Amber method. We have so many methods. We used for the other method also. We getting very less yield and the spectra also not good. Common was not few. So we started for the graphite using for the sodium nitrate and concentrated sulfuric acid and the cold water and using slowly KM4 and stir for the 7 hours. After stirring, you take the 1 portion KM4 and cold for the room temperature. You can add to the ice water with hydrogen peroxide. You will get like black color solutions. After black color solution, you do the centrifugation and sonication and wash with distilled water and sulfur like HCl 30% sulfuric hydrochloric acid and dry the overnight. We get corresponding the graphene oxide. The graphene oxide was further was confirmed by the IR spectroscopy. This OH was confirmed by the around like a 3460, around 3460. Remaining the C double bond O was around like a 1670, and remaining unreacted double bond, CC double bond around 600, 1600, and COH around peak is around 1250. So based on this confirmation, we recorded for the XRD other peak also. XRD is showing that spacing between these two layers around 9 is coming. Other studies also started for the Raman spectroscopy. Raman spectroscopy showed that this coming the two peaks. One is around 1350 and one more coming around 1590. This confirmed that lattice distortion is almost very good. So others like SEM is shown by the SEM image for graphene oxide. It is also image is very good compared to the what reported already. So we taken for this graphene oxide used for the same sequence and a TA and a A11 with the same two sequence used for the graphene oxide. When you start for the graphene oxide with whatever naturally occurring the DNA sequence, we started for the fluorescent emission spectra, like what you recorded before, the same I used for the 0.1 micromolar and same phosphate buffer solutions. But here particularly no detection for the metal ions. I used for the different metal ions. Metal ions 2 and metal ions 3 oxidations, there is no selective metal detections. Like you take the T1 and A1, there is very less for the, less than 10. Used for the remaining other metals like mercury and silver, calcium, cadmium, cobalt, also very less. You go for our artificial nucleic acid derivatives. You take the T1 and A1 was also very less compared to this one, very less. When you go for the graphene oxide, we got very good metal detections. When you go for the nickel, mercury, what you recorded same metal ions, I used for here also. When used for the graphene oxide, we got for the mercury chloride as a very good metal detectors. So what you modified artificial nucleic acid are useful for the very particularly mercury detectors. I used for the excitation 500 nanometers here. So I'm going to conclude for my talk. We synthesize for the L and D acyclic nucleic acid, and we confirmed by for the NMR mass spectroscopy, other studies. We used for that this modified compound we taken and used for the ruthenium complex. We used for the metal ion detectors. We recorded for the fluorescence and other studies. Then further we synthesis for the graphene oxides and is confirmed by the other studies and used for the this graphene oxide. So mercury detectors. This is my research group, like professor, this is my professor Aizan, my lab mates Lang and Rose, Srinivas, some other MSc guys. I will thank my professor for giving the postdoc questions and flowsheets. I will thank the collaborators for the Dr. Frank Sila from Germany, Tamil Mani for the Shanghai Institute of Technology, Organic Chemistry, China. This is deep calculations. I would like to thank our Department of Chemistry and other faculties, and particularly Professor Jodi is given for the good opportunity. Thank you all.
Thank you, Dr. Chandrasekhar sir, for your very wonderful talk on the construction of stable duplex by acyclic nucleic acid. On behalf of Department of St. Joseph's College, we wholeheartedly thank you, sir, for accepting our invitation as well as for delivering such a very wonderful talk. Thank you so much, sir. And before we conclude the session, we have a few questions for you. Let me ask you, sir. Sure. The first question: can this coupling of nucleic acid will be useful for doing RT-PCR test for converting RNA into cDNA?
Yes, sir, it is possible. We did not try particularly. We are focusing only for the DNA molecules. Some report is available where you can use for the natural DNAs.
Thank you, sir. Thank you so much. And we have a few more questions, but due to lack of time, we are running short of time. we try to conclude this session with this. Thank you so much, sir, for delivering this wonderful lecture. Thank you so much for your clarifications also. Thank you, sir.
Thank you, sir. Thank you, sir.
Now it is time for proposing vote of thanks. May I now invite Dr. Kanickai Raj, Assistant Professor of our department, to propose the vote of thanks.
Now it's a time for vote of thanks. Very good afternoon to all of you present on this platform, witnessing the international seminar on materials and technology for sustainable development, organized by the prestigious Department of Chemistry of this world-renowned Temple of Education, St. Joseph's College, Trichy. Above all, I would like to thank the Almighty God for His presence and blessings for making this webinar a successful one. I deem it a great honor and also feel privileged to propose the vote of thanks. First of all, I would like to express my deep sense of gratitude to Reverend Father Leonard Fernando, the rector, who is the mentor of this institution, and Reverend Father S. Peter, the secretary, who is the vibrant man of oratory, possessing the authority, and Reverend Father M. Arokiasamy, the principal of A++ accredited St. Joseph's College, who is the man of principle in achieving goal of success in every academic process. Thank you, dear loving fathers, for your support and guidance for this successful resounding webinar. I would like to express my profound thank you, dear loving fathers, for your support and guidance for the successful resounding webinar. I would like to express my profound gratitude to the convener and the dynamic head of the department, Dr. A. Peter Pascal Regis, and the co-convener and the vice principal of St. Joseph's College, Dr. S. Joseph Selvaraj, for their ideas and moral support at every stage of this webinar. I would also like to thank our beloved members of the organizing committee, Dr. A. Rose Venice, Associate Professor and Dean of IQAC, Dr. A. Irudaya Jodi, Assistant Professor, Dr. A. Simi, Assistant Professor, and myself, Dr. Kanickai Raj, for the meticulous planning and beautiful execution of this international webinar on materials and technology for sustainable development. I feel immensely happy to express my sincere thanks to all the staff members of the organizing committee for their contributions in making this webinar a grand success one. I would like to place on record my sincere and profound gratitude to Dr. Kanickai Raj, Professor of Physics, for his wonderful technical support for the successful conduct of this webinar without any technical issues or inconveniences. I take this opportunity to thank all the stalwarts, the great academicians, professors, research scholars, and the wonderful students from various institutions, from various universities across the nations, across the globe, for their active participation and overwhelming response, without which this webinar could not have been a successful one. Once again, I thank you all for your patience and cordial cooperation for these 2 days. Thank you very much. God bless you all.
Dear participants, feedback form is available in the chat box. Kindly give your feedback. Once again, we remind you, dear participants, feedback form is available in the chat box. Kindly give your feedback. Stay home, stay safe. Wish you all the very best. Thank you all. Sir, சொல்லுங்க சார். சார் சொல்லுங்க. போடலீங்களா? சார் போட்டாச்சா? சார் இப்ப வந்து சரிங்க சார். போட்டாச்சுங்களா? சார் இதை போட்டுக்கிட்டு இருக்காங்க சார். பேசுறீங்களா? ப்ளீஸ்